Alright, this is Algebra II, Chapter 6, Section 4, Rational Exponents. Okay, so if I had some variable square rooted, I can write it as a rational exponent, meaning instead of writing it as a square root with the radical symbol, I can write it with a fraction. And instead of calling it a square root of a, I can call it a to the 1/2. So remember, in the index for the square root, there's a 2 here. This 2 will be the denominator. So whatever we're going to root will be in the denominator. The reason why there's a 1 here is because a is to the first power. There's no root there. So let's do a couple of these. What if we had the cube root of a? That would be a to the 1/3. Again, the index would be your denominator. A to the 4th root would be a to the 1/4. A to the 5th root would be a to the 1/5, so on and so forth. If you got a to the nth root, it would be a to the 1/n. Okay, so whatever is your index is your denominator. Whatever you're rooting by is your denominator. Okay, so let's take that a step further. And let's say that we had a squared. And let's say I wanted to cube root it. So we still have a in the denominator of 3. So instead of it being a 1, it would be a 2. Let's say we had a squared to the 4th root. Again, a is still in the denominator, but now we have a 2. Now this could be simplified, and we could call it a to the 1/2, which is still the square root. That's still possible. We had a squared to the 5th root. So it would be a squared to the 5th power. You had a squared to the 6th root. It would be a to the 2/6, which could be the cube root, and so on and so forth. So we have a to the m, a to the n. That would be a to the m over n. Okay. Whatever is being squared or cubed or what have you is going to be in the numerator, whatever power is going to be raised to. And whatever the index is going to be in the denominator. So we can use a fraction form or rational exponents. It's the same thing. There's 2 ways to write it in radical form. So we did, a squared cube root. We can do that. Or you can say a to the cube root and then say that it's being squared. These 2 guys are equivalent. They are the same expression. Okay, these guys are equivalent. And you can sort of think of it as a to the, here, if we do PEMDAS, a to the 2/1 times a to the 1/3, which equals a to the 2/3, which is cube root of square a. So they are equivalent expressions. Okay. Alright, so they want you to write the simplified form of the expression. So 64 to the 1/2. Again, that's the same thing I'm doing square root of 64, which is 8. B, 11 to the 1/2 times 11 to the 1/2 is the same thing as saying 11 times 11 to the 1/2, which is 121 to the 1/2, which is the square root of 121, which is 11. Or you can think of it as once we get here, 11 times 11 to the 1/2 is the same thing as saying 11 squared to the 1/2. So in this case, when you have an exponent raised to another exponent, we can multiply. And it can be 11 2 over 2, which is 11 over 1, which is 11. You get the same answer. There's a lot of ways to think about these things. Let's see. We have 3 to the 1/2 times 12 to the 1/2. So you can think of it as 3 times 12 to the 1/2, which is 36 to the 1/2. Which is the square root of 36 if you want to do the radical, which is 6. That's one way of thinking about it. Another way of thinking about it is no, we'll leave it like that. That's a nice way of thinking about it. All right. All right, so similar to what we were talking about before, if I have some x to the m raised to the some index, I can make it an exponent and call it x to the m raised to the 1n. Remember here you're multiplying these guys, so it can be x to the m over n. Or these guys can be interchangeable. So the book says, okay, let's call it x to the 1 over n over m raised to the m power. So they switch these guys, which are fine because you're multiplying. So commutative property says we can switch them, which is fine. Then that says that we can call it the nth root of x raised to the m power. Okay, so what this is the proof of saying is that x raised to the m power nth root is equivalent to x nth root raised to the m power. These two guys are the same. They're equivalent expressions, and you can move them around. So these two guys mean the same thing. All right, so that's okay. Negative rational exponents. This should be fun. All right, so for 2a, we have w raised to the negative 5/8. To refresh your memory, if I have something raised to a negative power, that means I'm dealing with the inverse. So let's say w raised to the negative 2 power is 1 over w raised to the 2. And notice that the negative sign goes away after you reverse it from numerator to denominator. We're going to do the same thing over here. And that's going to be 1 over w raised to the 5/8. Now, if I was to, they want it in radical form, right? Yeah, they want it in radical form, meaning they want a some type of root. I could write it like this. So this would be the 8th root of w to the 5. I could. That's perfectly possible for me to do that. But here's the problem with that. And the problem with that is that I have a radical in the denominator. Right? I have a radical in the denominator, and I don't want that. So we would consider this not necessarily simplified. Not necessarily incorrect, but not simplified. So remember, we have to multiply it by some number so that I can have a whole number in the bottom, and what I do to the bottom, I do to the top. So since this is 5/8, I'm going to multiply this times w to the 3/8. Reason being is because 5/8 times 3/8, or w to the 5/8 times w to the 3/8 gives me w to the 8, or you could think of it as the 8th root of w to the 8th power. That's what we want. We want the 8s to cancel out, and then I'm just left with the w inside. That's what we want. What I do to the denominator, I'm going to do to the numerator. So that gives me w to the 3/8 over w to the 8/8, which is the same thing as saying w to the 3rd cube root of 8 over w to the 8th root of 8, which gives me the 8th root of w to the 3rd power over w. This would be my final answer. So for that fraction part down here, just to prove the point that it works with doing radicals, if I had w to the 5/8 root times w to the 3rd 8 roots, because I did it by using rational expressions, just to let you know that it works both ways. Remember, this is the same thing as saying 8 root of w to the 5th times w to the 3rd, which is the 8th root of w to the 5 plus 3, which is the 8th root of w to the 8. So it still works. It's easier to see it as a rational fraction, though, as a fraction, as opposed to using the radicals. Yeah. So that's 2a, 2b. We have w to the 0.2, which is 2/10. So it's going to be w to the 2/10, which is w to the 1/5, which is the fifth root, and w. Oh no, this is still a. 2a. Alright. 2b. What are the expressions in exponential form? Okay, so we have x cubed fourth root. So x, since it's being raised to the third power, the 3 goes in the numerator. Since it's being fourth rooted, the fourth goes in the denominator, x to the 3/4. And then for part 2 of that, we have y fifth root to the 4th power. Okay, y is being rooted to the 5th power, so we can write this as 5 in the denominator. Since it's being all raised to the 4th, we can write 4 in the numerator, and it's 4 y to the 4/5 power. And so here they have a problem where they're using, what is p? I guess p is years. And d is the distance from the sun, and d is being used in astronomical units. So p in years is equal to d in astronomical units raised to the 3/2. An astronomical unit is the distance for those science buffs who care, from the Earth to the sun. That's called 1 astronomical unit. Used a lot in astrophysics. So for part A, they give me that the distance is equal to 0.7 astronomical units, AU. So that's going to be 0.7 raised to the 2/3. So it doesn't matter which order you do it. So if you grab a calculator, you have 0.7 and you square it, then you cube root it. And I get 6.1 year. Oh, square rooted, I'm sorry. It's to the 3/2. I did it here to 2/3. No wonder I got a different answer. Alright, my fault. So it's 0.7 to the 3rd power square root. And you get 0.61. Oh, 0.72. You get 0.61 years, Earth years. And they asked for a Jovian year, which is a year on Jupiter. Oh, so this would be a Venus year. So a Venus year is 6.1 Earth years. How neat. And then for a Jupiter year, it would be 5.46 raised to the 3 house power. Which is 12.76. So 1 year, or for the one revolution around Jupiter takes 12 Earth years. One revolution around the Sun for Venus takes about a little bit more than half a year. Earth years. That's awesome. Nice information. Okay. All right. So properties of exponents all apply to rational numbers. So we did this in the prequel sections. A to the m times a to the n is equal to a to the m plus n. That applies to rationals too. You can add fractions as well. You can a to the m raised to the n is a to the m times n. Again, that applies to fractions as well. A times b raised to the m. That's the same thing as saying a to the m times b to the m. Again, applies to fractions too. We talked about raising something to a negative exponent. A to the negative m is equal to 1 over a to the m. When you divide exponents, you can subtract their exponents. This applies to fractions too. And then when you have some rational number raised to some exponent, a to the m, b to the m. Okay, so everything that applies to whole numbers also applies to fractions, fractions, fractions. They're all the same. So number 4. 4a. I have 3 square root times 4th root of 3. That's the same thing as saying 3 to the 1/2 times 3 to the 1/4. I could turn 1/2 into 2/4 to get a common denominator. So that's 3 to the 2/4 times 3 to the 1/4. Add their exponents. 3 to the 2/4 plus 1/4 gets me 3 to the 3/4, which is 3 cubed to the 4th power, or you can say the 4th root of 3 raised to the 3rd power. Then you have 4b. We have x cubed square root alpha x squared cube root, which is x to the 3/2 alpha x to the 2/3. I can multiply this guy top and bottom by 3, so this would be 9, 6. I can multiply this guy top and bottom by 2, which would be 4, 6. Then I can subtract x to the 9, 6 minus 4, 6. And that gives me x to the 5, 6. And again, I could write this in two different ways. I could say x to the 5th power to the 6th root, or I can say the 6th root of x raised to the 5th power. So hopefully you can build back up your fraction skills. If you done forgot your fraction skills, you might wanna revisit that in these types of problems. Alright, so 4C. We have 7 square root times the cube root of 7, which is 7 to the 1/2 times 7 to the 1/3, which is 7 to the 3, 6 times 7 to the 2, 6, which is 7 to the 3, 6 plus 2, 6, which is 7 to the 5, 6, which can be written in two ways. 7 to the 5th power 6 root, or 7 6 root to the 5th power. So that's 4. Alright, so they want us to write each number in its simplest form. So if we look at 5, we have 32 to the negative 3/5. Pretty sure that's 3/5. Yeah. That's the same thing as saying 1 over 32 to the 3/5. I could think of 32 as 2 to the 5th power. 2 times 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 times 2. Yeah. Is 2 to the 5th power. Raised to the 3/5. The 5's cancel. And I'm just left with 1 over 2 to the 3rd, which is 1 over 8. Now, if you're not comfortable with seeing the fact that 32 is 2 to the 5th, you can always do the 5th root of 32, and that would get you 2, and then raising it to the 3rd power that way. And that should still get you there. Five B, we have 16 to the 3/4. 16 can be considered 2 to the 4th power. Raised to the 3/4. These guys cancel. 2 to the third power, which is 8. Or again, like I said, you can fourth root 16, get 2, and then raise it to the third power. So 5c is 9 to the negative 3.5, which is 9 to the negative 3.5, which is 9 to the negative 2 times 3 is 6 plus 1 is 7. 7 halves, which is 1 over 9 to the negative, or not negative, to the 7 halves. 9 can be considered 3 squared. So 1 over 3 squared raised to the 7 halves. The 2's cancel. 1 over 3 to the 7th power. And I actually would be okay with that. But the yeah, I would be okay with that. 3 to the 7 is 1 over 2, 1, 8, 7. But that's what the book wants. They want actual number. What is each expression in its simplest form? Here I have 8x to the 15 raised to the negative 1/3 power. So we're multiplying these guys, right? So 8 to the negative 1/3 times x to the 15 over 3 negative, right? Because you're multiplying these guys, which is 1 over 8 to the 1/3. 15 divided by 3, that's x to the 5th power. I can rename 8 to the 1/3 as 2 to the 3rd times 8 to the 1/3 x to the 5th. These guys cancel, so I'm left with 2. So it's 1 over 2 x to the 5th. Yeah. So then 6b, I have 9x to the 4th root of y times 3 halves. I could turn, since I see a denominator of 2 here, that means a square root, I could turn this 9 into 3 squares. X times y to the 1/4, and then all that's being raised to the 3/2. So remember, I'm multiplying these out. So this 2 cancels out with that 2. So I have 3, and then the 3's cubed, times x to the 2/3, 3/2. Yeah, x to the 3/2 times y to the 3/4 eighths. Now, there's a couple routes to go from here. If we look at this x to the 3/2, it's an improper fraction. So I can break this up into x to the 2/2 times x to the 1/2, right? Which brings out this whole x. So x to the 2/2 is x. So I can say that this is 3 to the 3rd x times x to the 1/2, or square root of x, times the 8th root of y to the 3rd power. I would actually accept that. But the book kind of wants you to take it one step further. They don't want 2 different radicals. They want it under one big radical roof. So another way of doing it, and the way that the book wants you to do it, is to say, okay, and 3 to the 3rd is 27. So we have 27. This has a 3/8. This has a 3/2. I could multiply this top and bottom by 4. And now I have x to the 12/8 times y to the 3/8. Right, just like I said before, I could pull out x to the 8/8, which makes it x, and I have 4/8 left over, which is still 1/2. And I can say that this is 27x times x to the 4/8 times y to the 3/8. So now they both have the same denominator, meaning they could both be under the same radical sign. Then I can have 27x 8th root of x to the 4, y to the 3. So this is what the book wants you to write. They want you to put them all under one radical sign. Those two guys are equivalent expressions. The only difference is one has one radical sign that the whole thing is under, while the other one breaks it with the 2. I can see it both ways. For for the sake of sort of simplifying it under one radical, I can understand that. But to note, if you have an improper fraction, so a to the 5/3, that's the same thing as saying a to the 3/3 times a to the 2/3. So you can always pull out a whole number, which is a to the 1 times a to the 2/3, which is a times the cube root of a squared. Okay, this is fine. You can pull out a whole number if you wanted to. If you had like a to the 9/8. No, let's say 9/2. Right? So we could pull out a to the 4 to the 8/2 times a to the 1/2, which is a to the 4th square root of a. Perfectly fine. And actually, this would be considered simplified as over a to the 9/2. I would rather you write a to the 4th square root of a. Yeah. All right. That is that section. Hope you have a great rest of your day.